Hello everyone, and welcome to this Getting Started tutorial on Unity's new game AI behavior tree system, Muse Behavior. In this video, you'll learn the basics of this tool and how to give life to some guard NPCs so that they can react to the presence of the player, switch between different states, and even adjust their behavior dynamically via adjustable parameters. And by the way, if you want to get the complete demo scene and AI assets to analyze them in detail, don't forget that you can download everything for free on the Asset Store. And with that said, let's dive in. Before getting into our little guard example, let's quickly talk about the Muse Behavior tool itself. Muse Behavior is a new tool that Unity is developing to facilitate the implementation of NPCs or object behaviors. Its goal is to offer an easy-to-use visual graph-based interface to allow users to quickly compose and assemble little chunks of behavior and decision-making. At the moment, the Muse Behavior package is still at the experimental stage. There are already quite a few features in place to help us create behaviors, but there are also even more to come. In particular, for now, it focuses on behavior trees, although there are some tools that can be used to make state machine-like logics. But the team plans on adding other common AI techniques, such as utility-based decision-making in the future. From a more practical point of view, the tool creates behaviors that are presented as node-based flow graphs, read top to bottom, that can be debugged at runtime to clearly check why your AIs are acting the way they are. Each node in the graph contains the logic for a single step of the entire behavior, and as an all-behavior tree-based AI system, those nodes can be of two types. The inner nodes define how the logic flows through the tree, and which nodes should be executed now. And the other nodes, that here are shown in gray, define the actual actions to execute. Those actions can vary a lot, ranging from showing a game object in the scene to moving the AI agent towards a position, checking for the distance to another target, or storing some value for further computation. So, the logic flow starts at the very top, with the aptly named start node, and then flows down through the inner nodes to the action nodes, to really have the AI execute an action. Moreover, even though the node types are actually defined as C# classes in the project, the tool also offers some wizards and utilities to make it easier to create or edit node types. Most notably, in the graph, the nodes are shown as little human-readable stories where you can inject some context-specific data to actually power the logic. This is interesting because it makes the graphs both concise and easy to read for the AI designers. This context-specific data is then used in some unique way inside the C# class that defines the node type logic with one or more of the three possible hooks: the onStart, the onUpdate, and the onEnd method. Something nice is that you can always inspect the built-in nodes to understand how to code the logic, and then transfer your knowledge to create your own custom nodes by using the contextual menu in the graph editor. We'll see how to do this in more detail in the upcoming section. That being said, if a developer in your team already prepared all the necessary action nodes for your project, then, as a designer, you can simply play around with this library by bringing up the contextual menu in the Muse Behavior Editor and placing, connecting, editing, or removing nodes like you want. The data slots in the nodes can then be filled either with direct constant values or be linked to variables in the blackboard of your AI tree. This blackboard is the memory of the behavior tree. This is where you'll define all the variables you need to make decisions and inform your logic of the current context. These variables can be of various types, like basic integers, floats, and strings, or even a game object reference, or an enumeration with fixed values. The idea is then to get and set their values in your different nodes by integrating a data slot in the node story, linking your blackboard variable in it, and then using this reference in the node's C# class code. Other cool features of the tool include a simple system of event-based behavior triggers that can help optimize the logic flow, and the creation of subgraphs to better organize your AI logic in smaller reusable chunks. And as a little bonus, the Muse Behavior is also starting to incorporate generative AI features using ChatGPT, which we will discuss at the end of this video. Alright, so with this brief overview of the tool in mind, let's now explore how to use it to make a real-life example and give some brains to our little guards. First of all, because for now, the tool is still in the experimental stage, in order to download and install it in your project, You need to open the Package Manager window, click the plus icon, and use the Install Package by Name option to enter the unique code of the package. com.unity.muse.behavior. Once everything is imported, you can also import some samples to get some reference assets and better understand the basics of this tool. Those would be added as new startup assets in the project in the Samples folder. But here, to make our own Guard AI, we will rely on built-in nodes from the package itself and some nodes that have already been prepared beforehand. So let's simply start by creating a new AI graph and naming it Guard AI. Then we will double-click on it. Unity automatically opens the asset in the Muse Behavior Editor, and we are now ready to implement the logic of our AI. Okay, so now the question is, what behavior do we want exactly for our NPC guards? In short, we want our guards to react to the presence of the player in various ways. The reaction will be determined by how much stronger or weaker the player is compared to the guard, and by the field of vision of the AI instance. So the guards will have three possible states. If the player is nowhere in sight, then the guard will be idle and will walk along a predetermined path of patrol waypoints. If the player comes closer and enters the guard's field of vision, there will be two possible reactions. Either the player is weaker than the guard, and in that case, the guard will show a little marker to tell it's engaging combat and aim its weapon at the player. Or the player is stronger than the guard, and in that case, the guard will show a little scared marker and look for the nearest cover, where it will stay for a few seconds before coming back to its patrolling state. Of course, this behavior is not the most intelligent, but it will be quite interesting to study and tweak by changing some of the parameters on our player and guards, and to see how those changes affect their reactions. For now, let's start simple and work on the idle patrolling state of our AIs. As we said before, the logic flow of a Muse AI graph starts at the Start node, at the top. So before actually diving into the logic of our idle state, let's first make sure we have a way to switch between our three possible states, so that the graph executes the right behavior in the right situation. To do this switch, we obviously need to use an inner node to control the flow. And the good news is that the Muse Behavior team has prepared a nice built-in node called Switch to do just this. To add it in our empty graph, we simply have to right-click in the Editor Central area, go to the Add option, and, in the Flow subsection, select the Switch option. This instantly adds the Switch node to our graph, and we can now connect it to the Start node so that when it executes its logic, our AI starts by checking which state it is currently in. As you can see, this node has a data slot, which obviously expects a value for the state variable to switch on. And it expects this variable to be an enumeration, with a fixed list of possible values. To create such a variable, we need to go to the Blackboard panel on the left, click the plus icon, and then go to the enum variable type. Here, we can create our new enumeration type, which we can call Guard AI state, and which will take one of three values: idle, attacking, or fleeing. This wizard is a way for us to create this new C# enumeration automatically, but at this point, we haven't yet used this new enumeration type in our graph. So we now need to come back to the Blackboard and create a new enumeration variable based on our new type. We'll name it state, and finally, we'll use it in our switch node to pick the logic to execute depending on its current value. To do this, we just need to click on the link icon next to the data slot in the node and select our variable. You see that as soon as we pick our enumeration variable, the switch node gets new autochild nodes, one per possible value, to allow us to create and connect sub-branches for each case. All right, now that our main switch is ready, we need to actually implement the logic for our idle state. To begin with, let's right-click in the Editor Central area and go to the Add option. There, we can use the search bar at the top to get our readily available patrol node and use it directly for our idle movement. When we add it to our graph, we then see that this node has three data slots. First, we need to specify the agent that will patrol, in other words, our guard himself, which we already have referenced as the self-Blackboard variable in any Muse behavior graph. Then, we can create a new Blackboard variable of float type called speed, with some default value, and at the end, link this speed variable to specify how fast the AI should walk along the patrol path. And finally, we need to pick the waypoints positions to use for this patrol. Because, for now, the Muse Behavior tool doesn't yet support arrays or lists as Blackboard variables, this node expects us to pass in the reference of a game object that contains all the waypoints as children. For this, let's start by creating a new Blackboard variable of type game object in our graph called waypoints and assign it in our node. Then, let's go to our scene and create a few empty game objects around one of our guards, grouped under a waypoints parent. Finally, we'll select our guard in the middle, give it a new behavior graph agent script component, and fill in its Blackboard variables in the inspector. For the self slot, you see the guard game object itself has automatically been assigned. For the speed, we can leave the default value of 4. And for the waypoints, we'll drag our new parent waypoints object. At this point, we have a first runnable version of our AI logic. So let's play our scene and see how it looks. You notice that the guard indeed starts moving, but it is just sliding on the ground instead of really walking, and it gets blocked by the objects in the scene, since it's going in a straight line from waypoint to waypoint. And that's because, currently, our patrol node doesn't consider animations, and it is using its default translation-based mode, meaning that it doesn't take this whole terrain into account at all. Luckily, this terrain was prepared as a nav mesh beforehand, and it has already been baked. So the nice thing is that it is actually extremely simple to fix our agent's movement. We just need to come back to our Muse behavior graph, select the patrol node, and open the node inspector. Here, we can see some extra parameters for our node that aren't shown by default, but can help further customize its logic. And typically, here, if we toggle on the Use NavMesh option, then the patrol node will automatically try to find a NavMesh agent component on the self-referenced object and use it to move the AI from point to point while following the terrain surface. By the way, this is also where you can choose how long the agent should stop at each waypoint and where you can give it a reference to a game object with an animator if you want to have the character play an animation while it is walking. Note that for this specific pack of assets, playing animations requires a bit of setup, so we also have to add a few nodes at the very top of our graph to prepare its rig and animator. And with these simple modifications, we can now run the game again, and we see the guard now properly walks from one waypoint to the other with a nice animation and stops for a little while at each one. To properly examine what is happening, we can also look at the Muse behavior window and at the top, go to the debug tool and select our guard. You see that now the graph shows the flow of logic in real time, while the game is running, which makes it easy to understand which actions are executed and why. The next step is to have our guard check for the player, and if we're close enough, evaluate the threat to transition to either the attacking or the fleeing state. Once again, for this, we can take advantage of a nice built-in node of the library that checks if the distance between our agent and another object is below a certain threshold. So here, we can reference our agent, create another game object variable in the Blackboard for the player, and a float parameter for the AI's field of vision, and use both those new variables in the node's data slots. And then we simply need to execute both those nodes in parallel so that, while the guard is patrolling, it also looks around for the player. We can use the run in parallel until any succeeds built-in node, because when our check will pass, we'll change the state of the AI anyway, so we won't be continuing in this branch. But of course the question is, how exactly do we get our player? Should we drag our object into this slot for each guard in our level? A better solution is to auto-find it based on its tag, which is the built-in player tag when our AI logic is first initialized. To do this, we'll go at the beginning of our AI graph, before our state switch node, and add a new find with tag node. We'll assign the result to our player variable and look for the player tag. Our logic can now spot if the player is close to the AI instance. If it is, then it will return a success and trigger any nodes that are put after this one in the sequence. Else, it will abort early and have the AI ignore the rest of the actions in this sequence. This means that all we need to do is, if this node succeeds, run one last node that evaluates the player threat and decides what state to switch to. Except that this time, we don't have a ready-made node for that. So we're going to have to create our own custom node to handle this player threat evaluation. To create our custom AI node, let's start by right-clicking on the central area of the Muse Behavior Editor. Then, we'll pick the Create New Action option, and this gives us a wizard to specify the base info of our node. This wizard is a stepper that lets us create our new node type gradually. So first, in this start screen, we can specify its name. Here, we can put Evaluate Player Threat. Note that you can also choose a special category if you want your node to be sorted in some subgroup in the contextual menu, or you can leave it to the default action value to have it be at the root of the list. Then, if you click on the Next button, you get to the second screen where you can write the story of the node. This is the most important thing. This determines both how the node will appear in the graph and what data slots it will have. The idea is to start by writing a little descriptive sentence for our node in natural language. And then, for some of the words in our description, we will change their type to transform them into data slots. You also notice that when you use a word that is exactly the same as the name of one of your Blackboard variables, it is automatically changed to a data slot of the right type. More precisely, in our case, the agent, the player, and the state should be data slots, because those are the ingoing and outgoing data connections that we need to read from or write to in our node's logic. And finally, we can create our new node type, either manually or using generative AI features to auto-create the base of the node's logic. For now, we'll ignore this ChatGPT-related flow and simply click on the Create button. You see that the Muse Behavior tool auto-generates a new C# script for us that defines the logic of our node. For now, it has the story we just defined as an attribute, the data slots we asked for as Blackboard variable fields, and some empty overrides for the 3 possible entry points for a node logic: onStart, onUpdate, and onEnd. The point of this node will be to compare the scale of the agent to the one of the player. If the agent is smaller, then it will consider the player like a big threat and switch to the fleeing state. Otherwise, it will switch to the attacking state. To have our logic be executed in real time, we can implement it in the onUpdate function. So let's simply remove the other ones and, in here, get the scale of both our objects. To access this data, we first need to take our object reference from the Blackboard variable, for example, the agent data slot, and then use its value property to get the actual object. So here, agent.value is a game object, and then we can just use the usual transform.localScale syntax to get its size. We can do the same with the player Blackboard variable, and then we simply have to compare those two floats. If the agent is smaller, it will change the value of its state Blackboard variable to fleeing. Else, it will change it to attacking. And finally, we'll return a success at the end of the function to tell the graph this node has finished executing, and all went well. By the way, it can also be a good idea to check all the variables have been properly initialized before trying to do anything, and if there is any issue with our references, return a failure and abort early. With our script ready, let's come back to the graph, instantiate this new node type in the AI's brain, and fill in the slots. Finally, we'll drag this new node after the one that checks for the proximity to automatically chain them in a sequence and have them be executed one after the other when the graph is updated. This way, if the check fails, the graph will stop there and just continue executing the patrol node in parallel. But if the check passes, the graph will run our Evaluate Player Threat node, switch the state of the guard, and then exit this sub-branch. And to have it restart its logic from the top and branch out to the new state the next time, we should also make sure our start node has the repeat option enabled. Though, if we try to run this behavior tree, we will quickly realize that the check isn't working properly. And the problem is actually not in our code, it is in our graph structure. The thing is that for now, the tool works like this. If a node fails, it is stopped and doesn't run again until it is restarted. And for now, there is nothing in our tree that restarts it, because our parallel node doesn't do this automatically. The solution is to add a modifier in between our parallel node and the actual action nodes to have them repeat and restart again and again while the game is running. For the check, we can actually use the repeat until success node, since we don't want it to keep going if it succeeds. Similarly, to have the patrol run continuously while we're doing our checks, we can give it a repeat modifier node with no success or failure condition, to have it be executed again and again and continue the patrolling movement. So, in the end, we get this logic for our idle state that has the guard patrol along its set of waypoints, and then as soon as we come closer, switch to another state, depending on the relative scale of each opponent. And the cool thing is that this comparison is done in real time, so we could have some external system, like an input manager, have our player character grow or shrink, and the AIs would react accordingly at any given point in time. Or we could change the size of the field of vision of the guard in the inspector, or with some UI slider to tweak how close we can get before this state change triggers. Now, with our idle logic ready, let's move on to the attacking state behavior. For the attacking logic of our guard, we won't do a step-by-step study of how to create, link, and fill in the nodes, because it is mostly equivalent to what we have already done. Rather, let's have a look at the pre-implemented logic and take this opportunity to talk about a few extra interesting concepts of behavior trees. The attacking state also starts with a parallel flow node, because the point will be to have the AI execute a series of actions while continuously turning to look at our player avatar. So these two branches on the right with the animator update and the repeated look at behavior handle the continuous follow of the player, and the real meat of the attacking logic lies in the sequence subtree on the left. As in all behavior trees, the goal of this sequence is literally to chain several actions one after the other, and make sure you don't move on to the next one until the current one has succeeded. Here, the idea is the following. First, with the left sub-branch, we interrupt the guard navigation. We hide the fleeing-related marker. We toggle a little marker above the head of the guard to show it is attacking, and then we use a custom node to update its animation rig and have it point its weapon at the player. Then, the middle branch uses a repeat node and an inverter modifier to interrupt this state as soon as our player avatar gets outside the field of vision of the AI. Note that we could also use the built-in check is further than node instead, and it would be absolutely equivalent. But the interesting thing with using the inverter modifier is that it shows us the modularity of the tool, which is a core concept of behavior trees. Indeed, behavior trees let you reuse your nodes in various places, like a little library of building blocks that you rearrange to create ever new behaviors. Finally, the last branch in our sequence, on the right, just switches the AI back to its idle state. This simple study also shows you something very cool with behavior trees, graph-based AI tools in general, and Muse Behavior in particular, which is that they are quite easy to read. And here, the little stories of each node really make for a user-friendly representation of our guard's logic. So if we run our game at this point and make sure that our player avatar is not bigger than our guard, then we see that the AI first patrols in its idle state. Then, when we get in its field of vision, it switches to the attacking state, shows a little red exclamation mark, and finally points its weapon at our avatar. It also continuously turns to look at us, thanks to our parallel execution. Finally, if we take a step back and get out of its field of vision, the guard exits its attacking state and goes back to idle, which causes it to restart walking along the patrol path. And now, to wrap up this tutorial, we need to take care of the last state of our guard, the fleeing state. For this last branch and this last section of this demo, we're going to take a look at one of the most interesting features of Muse Behavior, the generative AI. In a nutshell, these are extra tools that are available in Muse Behavior if you've joined the Muse beta. They are bonus helpers that allow you to create either node logic or tree structure by writing a little text in natural language, and then having the computer auto-generate it for you thanks to ChatGPT under the hood. To use it, we just have to right-click in the central area of the editor and choose the Create Subtree from Text option. This brings up a new pop-up where we can enter our prompt, or in other words, the description of the tree structure we want to generate. Here, the goal will simply be to describe the behavior we want for our guard when it is in this fleeing state. So, for example, we can input something like this. First, self resets its movement. Then Self looks at the player. Then it toggles its exclamation mark attack off, and it toggles its exclamation mark fear on. Then it waits for 1 second and toggles the exclamation mark fear back off. Then it finds the closest cover spot object with the tag cover spot, and it moves to this cover spot with its current speed. Finally, it waits for 2 seconds and switches its state variable back to idle. And that's it. If we click on the Create button, we see that Muse then thinks for a while and eventually creates a new sequence of nodes in our graph with a series of actions to execute one after the other. And you see that overall, it's really close to what we would have done ourselves. Now, as we've said before, it is not yet perfect. You may have some data slots that are missing their links, especially if they are only accessible via the inspector because they are hidden. Still, the structure in itself is fairly good, and the basics of the logic are there, with just a little prompt and a few seconds of generation time. So this ChatGPT-powered AI creation system, even if it is not yet perfect, is already extremely cool. And it may eventually be a very powerful way of setting up or boosting behaviors very intuitively, without having to manually design or code all of your AIs. To sum up, Muse Behavior is a brand new built-in AI tool for Unity that will make it easy to give life to your NPCs and your environments, and overall take advantage of the power of behavior trees. Its easy to read and easy to use graph-based editor will make it accessible to everyone, and its ChatGPT-related features will allow for quick AI design for all of your projects. So if you're curious about this project and you want to check it out in its current version, don't hesitate to download the demo scene that goes along with this tutorial and keep an eye out for even more cool features.